In this crash course program lecture, we will discuss mechanical properties of solids and fluids. This important chapter has three parts: mechanical properties of solids, mechanical properties of liquids, and the third part is hydrostatics and hydrodynamics. First, we will take up the mechanical properties of solids. This is also known as chapter elasticity. So we call it as elasticity because this is all about elastic properties of matter. What are all the important features of this chapter? Let us go through this one. First of all, stress. Whenever an object is subjected to an external force, there may be change in dimensions of the force, the change in dimensions of the object. And due to this tendency of change in dimensions, the object tends to restore. This internal restoring force is interpreted in terms of stress. This stress is the ratio of internal restoring force, which is developed inside the object or material, divided by area of cross section. This is the ratio of internal restoring force to area of cross section, or we write it as F divided by A. Remember, this is restoring force, the internal restoring force. So stress is equal to force divided by area. There are three types here. One is what is called as tensile stress. Tensile stress is seen whenever an object is under the influence of a force which tends to elongate an object. This is generally what is known as, first is it's actually longitudinal. In longitudinal, we have tensile and we also have something known as compressive. So what is tensile? For example, let us take a simple object of a rod which is fixed at one end, and let's put a load on that. For example, I am attaching a load. Then this force, external force, tries to pull it along this direction, while the tensile stress, that is restoring force, tries to pull it along this direction. That's right. Thus, there is a stress. Likewise, if I consider a rod which is fixed here to the wall, and I apply a force along this direction, and the restoring force tries to pull it back. In the case of compressive stress, suppose there is a rod and I try to push it, or let us take a cylinder which is kept on a surface and I am trying to apply an external force. So in both the cases, there is a force which is tending to, you can notice there is a force which is tending to elongate, which is in the opposite direction. This is what is called as compressive stress. This is compressive stress. And the second is what is called as, this is longitudinal, and the second is what is called as volume stress or bulk stress. Here an object is under the influence of a force which tends to compress a given object or say expand a given object. For example, let us take say a cube. Here is a cube on which I apply an external force. For example, you can take this cube inside say a liquid. Then the object gets compressed. These are the new dimensions of the object. You can assume that the object is compressed, and thus there is a change in the volume, right? And we can consider one more example. For example, a sphere is pushed inside liquid, it gets compressed from all the sides. There is a change in its dimensions as well. So, volume stress is basically the stress developed when forces are extended or say applied from all the sides. The third is what is called as shear stress. Let's try to understand what that shear stress is. Tangential stress or shear stress. So, in the case of shear stress, an object is fixed at its bottom, for example here, and we are applying the force from its sides. It is pushed like this. For example, there is a force which is tending to push it like this. You can think of a stack of books one placed over the other, and a force tries to push it from the top. And finally, the shape of this object will be something like this. You will have the new object, or say the object will get this shape. This is the shape of the object. So, under the influence of this, the object changes its shape like this. Or you can think of wringing of clothes. So, the three stresses are, first of all, tensile, compressive, tensile and compressive, and the second is volume stress, and the third is tangential stress. Now, the idea of strain tells us what is the change in the dimensions of the given object. So, according to which strain is equal to change in dimensions of the given object divided by original dimension. Again, we have three types here: longitudinal, tensile or compressive, which is equal to change in the length. It may be elongation or it may be compression, change in the length divided by original length, which is equal to delta L divided by L. Likewise, we have bulk strain, which is equal to change in the volume divided by original volume, which is equal to delta V divided by V. So, change in volume divided by original volume. Third is shear strain. So, in the case of shear strain, the idea is like this. Suppose we consider the previous example. In the previous example, if I take L as this dimension, and let us assume that finally this takes this shape, this is L, this is theta. Let us assume that this is L and this is theta. Then the shear strain is given by tan phi is equal to L divided by L. Tan phi is equal to L divided by L. So, this is basically displacement of the upper wire or upper face of the wire or upper face of the cube divided by distance between the two faces. If theta is small, you know how to write. If theta or say phi is small, I will take it as theta. If theta or phi is small, then we can write for small theta, theta is equal to L divided by L. That is the case of shear strain. So, shear strain is given by the ratio of displacement of the upper face divided by distance between the two faces, one fixed face and the top face on which the force is applied. Now, whenever a stress is, or say whenever a stress is generated in an object, there is a strain, or say because of strain there is a stress. We can relate each other, of course. Now, if I consider an object, maybe a wire, on which some force is applied, we can find out the relation between the stress and strain, and we can plot a curve between these two. So, what we will do is, we will take a wire and we start applying the force, and we will find out what is the nature of the curve. At the beginning it is linear, the curve is linear. That means within a certain limit the stress and strain are directly proportional to each other. Afterwards, the stress and the strain are not directly proportional to each other. The limit up to which these two are directly proportional to each other is called as elastic limit. This is known as elastic limit. Now, beyond that, the stress strain graph is somewhat like this. This is the nature of the curve, and this is actually elastic region. The first is your elastic limit, the second is elastic up to certain value. That means up to this you can say that the object can get back to its original region. Now, beyond that, the object becomes permanently deformed, and we call it as plastic region. So, there are two regions, one is elastic region and the second is plastic region. In the elastic region, the object can gain its dimensions back. Plastic region, there is a permanent deformation, and the maximum value beyond which the object snaps is called as breaking strength. This is known as breaking strength. And we observe that within certain limit the stress and strain are directly proportional to each other. So, stress is directly proportional to strain, and this is what is called as Hooke's law. So, according to Hooke's law, within elastic limit, stress is directly proportional to strain. Or we can write stress is equal to some constant of proportionality into strain. This constant of proportionality, whatever appears here, is known as modulus of elasticity. It's known as modulus of elasticity. So, what is that modulus of elasticity? It is basically the ratio of stress to strain. And this is constant for a given material. It depends on the nature of the given material. It's the property of a given material. So, it is the property of a given material. There are three types of moduli of elasticity. We have, first of all, Young's modulus of elasticity. Which is tensile stress or longitudinal stress divided by longitudinal strain. We can write it like this: F divided by A divided by delta L divided by L. Second is bulk modulus of elasticity, which is represented by B or K, any symbol is used, and this is volume stress, bulk stress divided by bulk or say volume strain, according to which this is F divided by A divided by volume strain is delta V divided by V. Most of the times this happens to be negative, because the object is under the influence of compressive forces, it's negative. So, bulk stress is generally treated as negative, or say bulk modulus of elasticity is treated as negative. third is what is called as rigidity modulus or shear modulus, according to which this is shear stress divided by shear strain, that is F tangential divided by A divided by phi. So, these are the three types of moduli of elasticity. These are the three types of moduli of elasticity. There are a couple of important things to be kept in mind here. Suppose I consider, say, a wire. Let us consider the case of a wire. Let us assume that L is the length of the wire, be suspended like this, and let us assume that a weight mg or say mass m is suspended from this wire. Then we can say for this wire, area of cross section being A, Young's modulus is equal to stress divided by strain. What is that stress? It is F by A. This is delta L divided by L. F is nothing but mg, mg divided by A divided by delta L divided by L. A is nothing but pi r square. So, we can write mg divided by pi r square, where r is the cross sectional radius, divided by delta L divided by L. So, for a rod or for a wire, light wire, the Young's modulus can be understood in terms of this equation. Remember, this is a light wire. Suppose I consider a wire which is thick. Let us assume that here is a thick wire, and this thick wire elongates under its own weight. Let us assume that this wire of length L, whose cross sectional area is A, elongates under its own weight. Let us assume that delta L is the increase in its length due to its own weight. Then the increase in its length under the influence of its own weight is given by mgl divided by 2ay. Remember this one. This is mgl divided by 2ay. Many times this equation is also written like this. Mass can be written as density into volume. So, density into volume, that is AL, and this is L, and G is there, of course, divided by 2ay. So, notice that this eventually becomes rho G L square divided by 2y. Thus, the increment in the length of a rod due to its own weight is given by this one. So, under the influence of its own weight. So, under the influence of its own weight, the increment in its length is given by this expression. Let us consider one more example. Suppose I consider a gas, and a gas possesses bulk modulus, because most of the times it is the change in the volume. Let us see how does or what is the bulk modulus for a given gas for different processes. For example, let us assume that it is isothermal process. For isothermal process, PV is constant. That gives us PdV plus VdP is equal to constant or 0, differential of this 0. So, we have P is equal to minus dP divided by dV by V. So, bulk modulus is equal to P, because bulk modulus is equal to F divided by A divided by minus delta V by V or delta V by V. And this itself is B. So, F by A has the dimensions of delta P or dP. So, for an isothermal process, this is the equation. What about adiabatic process? For an adiabatic process, you know, PV to the power of gamma is constant. So if I differentiate it, P V to the power of gamma, gamma V to the power of gamma minus 1, correct, into dV plus V to the power of gamma dP is equal to 0. And we can simplify it further. Gamma P dV is equal to minus V dP. Or we have dP divided by dV by V with a negative sign is equal to gamma P. But you know, left hand side is nothing but bulk modulus. So bulk modulus during adiabatic process is gamma P. You studied it while doing speed of sound in gaseous medium. You may wish to recall Newton's formula and Laplace's correction, etc. deal with this concept. Suppose I consider isotropic process, or sorry, polytropic process. Polytropic process. For any polytropic process, you know, PV to the power of x is constant. So similarly, I can write x into P V to the power of x minus 1 into dV plus V to the power of x dP is equal to 0. That gives us minus dP divided by dV by V is equal to xp. But this is bulk modulus, so bulk modulus is equal to xp. So in general, we can write bulk modulus as xp. One another important aspect here is the idea of compressibility. What is compressibility? Remember, it's the ratio of or reciprocal of bulk modulus. So we have 1 divided by K or 1 divided by B as the expression for this one. Couple of important results here. Number 1, Poisson's ratio. Sigma is equal to, it is lateral strain divided by longitudinal strain. Let us consider an object which is fixed, or say fixed at one end, or say let us consider a wire, anything is fine. And the wire is of length L. We want to stretch this wire by delta L by applying a force F. Now the question is, how much work has to be done in order to stretch a wire? Some amount of work is to be done. The work done is given by half stress into strain into volume. This is many a times written like this. This is equal to half F by A, strain is delta L by L, volume is AL. So this AL and this L cancel, leaving half F delta L. So work done is given by half F delta L. This can also be interpreted in a different way. Look at this equation. I am going to write as W divided by volume is equal to half stress into strain. But you know, work done increases its potential energy. So I can say energy stored per unit volume, that is energy density. Volumetric energy density is equal to half stress into strain. Half stress into strain gives us the expression for energy density of a solid. One another important result is about a rod which is fixed between two rigid supports. For example, there is a rod whose length is L, coefficient of linear expansion is alpha, and the cross-sectional area is A. Here, thermal stress, you have done it while doing thermal physics. Thermal stress is given by alpha y into delta theta, where delta theta is the change in temperature. And strain, thermal strain is given by alpha delta theta, and thermal tension, that means the actual force, is given by alpha y A into delta theta. It comes from the definition of y. Y is given by F by A divided by delta L divided by L. So thermal stress is alpha y delta T. Strain is given by this expression, while tension is given by this particular expression. So these are some basic ideas as far as the ideas of properties of solids is concerned. These equations play an important role in solving numerical problems. Keep these equations in mind. Now let us take up properties of fluids. There are two important properties. One is the idea of surface tension. Second is the idea of viscosity. We will take up surface tension and viscosity one by one. Surface tension is the property because of which the exposed surface tries to contract and it tries to have a minimum surface area. This is the idea of surface tension. Suppose I consider intermolecular forces. Intermolecular forces are of two types. Between the molecules of a given liquid, it is cohesive force, while molecules of different kind exhibit adhesive force. These properties are basically the properties which decide this surface tension. So, surface tension, these are key important things. It is a scalar quantity, and remember, it is always tangential to the liquid surface. It is always tangential to the liquid surface. And surface tension is always produced due to cohesive force. And if the cohesive force is more, surface tension is also more. Whenever the surface area of a liquid increases, the molecules from the interior of the liquid rise to the surface. So, work has to be done against the downward cohesive force. For example, if I consider, say, this idea, this is a liquid surface. Let's consider this way. So, what we are trying to do is, we are trying to increase, say, the surface area of this part. Increasing the surface area means pushing some molecules from inside to the top. Now, pushing from inside to the top requires work. Work against what? Work against the downward cohesive force. Cohesive forces tend to pull it back. and we have to push the molecules or molecules from inside to the top, as a consequence of which the work done gets converted into internal energy. That is what is nothing but surface tension. Suppose I consider, say, a liquid surface on which we consider a line. Then the surface tension is nothing but the force which is tangential divided by the length of that imaginary line. So, force acting per unit length of an imaginary line drawn to the free liquid surface at right angles to the line and in the plane of the liquid surface is defined as surface tension. So, it's basically force acting per unit length of an imaginary line drawn on the liquid surface. Suppose I consider a couple of important concepts related to this one. As I was telling, the work done gets converted in the form of energy, and this is what is known as internal energy or the surface energy. Surface energy increases by a value T into delta I, where T is the surface tension and delta I is the increase in area. So, in fact, we can write surface tension as increase in its surface area, increase in its internal energy or surface energy divided by increase in its area. So, this is the work done. This is the work done to do so. There are many important applications as far as this simple concept is concerned. Let us see what are all the important concepts, important equations, important applications, etc. Number one, in order to do work, in order to increase the area, or say in order to find out the energy associated with different say shapes. For example, if I consider a liquid drop, for a liquid drop the work done is equal to 4 pi r square T, or we can write corresponding increase in the energy is 4 pi r square T. However, for a soap bubble, this W is 8 pi r square T, or delta U is equal to 8 pi r square into T. Let us consider such a big drop. For example, here is a big drop whose radius is r, and we want this to be split up into n identical drops, each of radius r, say. Then again work has to be done. What is that work done? Work done is equal to change in the surface energy, and this becomes change in the surface energy can be calculated, and to find out it we need to relate the radii, and clearly you all know that r is equal to n to the power of 1 by 3 into r. Thus change in surface energy becomes delta U is equal to 4 pi r cube into T 1 by r minus 1 by capital R. This can be simplified further, 4 pi r square T into n to the power of 1 by 3 minus 1. So, the work done in such a case is given by this expression. If I consider such a liquid drop, or maybe a bubble, or maybe a cavity inside liquid, etc. There is an excess pressure. Suppose I consider this concave side. The pressure on the concave side is greater than the pressure on the convex side. The pressure on the concave side is greater than pressure on the convex side. Now, you may ask, by what value is this pressure greater? This is something like this. Suppose I consider a liquid drop. In the case of a liquid drop, then the pressure inside is greater than pressure outside by a value 2T by R. That means pressure inside is greater than pressure outside by a value 2T by R. This difference is what is called as excess pressure, and excess pressure for such a case is given by 2T divided by R. Suppose I consider a soap bubble. That means this is a surface, or say soap bubble, I will write as soap bubble, and this soap bubble has two surfaces, inside and outside. It is hollow, remember. This time the pressure inside is greater than the pressure outside by a value 4T divided by R, or the excess pressure is equal to 4T divided by R. So the excess pressure is equal to 4T divided by R. Suppose I consider a cavity. For example, you have a liquid, this is liquid, and an air bubble, or say a cavity is generated here. Cavity is nothing but air bubble. Now if you look at it, here again there is only one surface, and accordingly the excess pressure in this case is 2T divided by R. So excess pressure in this case is nothing but 2T divided by R. Thus, for a liquid drop, it is 2T by R. For a soap bubble, it is 4T by R, and a cavity or air bubble in a liquid, it is 2T by R. What do you observe? You observe that if there is one surface, then the excess pressure is 2T by R. If there are two surfaces, then it becomes 4T divided by R. So remember this important concept, a very useful idea for numerical problems. The relative values of the adhesive force and the cohesive force decide, or say give rise to, probably non-flat meniscus. For example, if I consider say a liquid in contact with a solid. If I consider this particular point, this is under the influence of two forces, cohesive force and adhesive force. Adhesive force is by the solid, cohesive force is by the liquid molecules. If the cohesive force is greater, suppose assume that cohesion is greater than adhesion, then the liquid takes this shape at the meniscus. If the adhesion is greater than cohesion, then the liquid meniscus takes this shape at the point of contact, which means that it is not a perfectly flat surface at the point of contact. Suppose I consider this simple case. Let's assume that at the point of contact, the liquid surface is like this. We can draw a tangent at the point of contact inside the liquid. And this angle is what is known as angle of contact. So I have drawn a tangent at the point of contact between, or say with respect to the liquid in contact, and I measure the angle. Angle between what? Tangent and the plane surface of the solid. This is what is called as angle of contact. That is nothing but the angle enclosed between the tangent plane at the liquid surface and the tangent plane at the solid surface inside the liquid. This is angle of contact. Suppose I consider a concave shape outside it is concave. For example, this is the shape. Then the liquid rises up. That means this time theta is less than 90 degree. You may notice that this theta is less than 90 degree. So angle of contact theta is less than 90 degree if the concave shape is up and the liquid rises up. Suppose you have this case. Then this is the tangent and this is your angle. So this time it is convex shape up and it falls, the liquid falls down, or say there is a drop, and theta is greater than 90 degree. Third case is the meniscus is flat. For example, here you can consider the meniscus to be flat. So this happens and the liquid neither rises nor drops. There is no rise, there is no drop, and it gives rise to theta is equal to 90 degree. So angle of contact is this particular angle. Now we saw that the liquid may rise here, isn't it? For example, if I consider this, there is a rise in the level. Suppose I consider a very narrow tube. If I consider a narrow tube, then what happens is that because of this angle of contact, the liquid level actually starts rising. Actually, it is to balance the excess pressure. So what happens is that whenever a capillary is immersed, there is a rise in the level of the liquid inside this capillary. This is what is called as capillary rise. And that capillary rise H is given by 2t cos theta divided by rho r g. Capillary rise is given by 2t cos theta divided by rho r g. What is that? Rho is the density of the liquid, r is the radius of this capillary tube, r is the radius of the capillary tube, g is the acceleration due to gravity, t is the surface tension, and theta is the angle of contact. This height is measured from the bottom of the meniscus. However, there exists some liquid above this line also. So if the correction is to be taken into consideration, so what happens is something like this. So if I take this into consideration, this is your H, that is what this expression is. But if I take this actual H into consideration, then if this correction is applied, then this T, surface tension, can be written in the corrected form like this. This is rho r g into H plus r by 3 whole divided by 2 cos theta. So taking the correction into consideration, then the surface tension can be written in the following form. One of the very important ideas here is something like this. Let us consider two soap bubbles. For example, this is a soap bubble of radius r1 and there is one more soap bubble of radius r2. Now, let's assume that say r1 is greater than r2, this is r1 and this r1 is greater than r2. Now, when they are brought in contact with each other, what happens is that they form something known as a double bubble. That means it's something like this. And these are their actual surfaces. Now what happens is that the pressure inside the smaller is greater. Now excess pressure is inversely proportional to radius, So pressure inside this is greater and therefore it exerts a greater pressure. Therefore now this is the common meniscus. So this becomes the common meniscus for both of them. So if I consider this bigger sphere, or say the sphere corresponding to the common meniscus, remember this is R2, this is R1. This common meniscus will have a radius R, which is given by R1 R2 divided by R1 minus R2. So this is the radius of curvature of the common surface. So common surface which is in contact will have a radius as given by R is equal to R1 R2 divided by R1 minus R2. So this is basically a double bubble case. That means if you consider two bubbles joining to form a double bubble, this is the case. However, if the two bubbles, for example, if I consider this is a bubble of radius R2, this is another bubble of radius R1. If they combine to form a bigger one whose radius is R, then their radii are related simply by this equation. R square is equal to R1 square plus R2 square, or R is equal to square root of R1 square plus R2 square. So this is the idea behind the combination of bubbles. Another important property of a liquid is what is known as viscosity. Simple idea. Viscous force is nothing but the force between different layers of a liquid. For example, if I consider different layers of a liquid, let's assume that these two layers have a velocity separation delta V, and correspondingly this height is say delta Y, then viscous force is directly proportional to velocity gradient. And Newton's law of viscosity tells us that this force is given by eta A dV or delta V divided by delta Y. For small values, this can be written as dV by dy. So viscous force is given by eta A dV divided by dy. This is what is known as Newton's law of viscosity. The couple of important equations here. Suppose I consider a pipe or say liquid flowing here. Let's assume that Q is the amount of or say volume of the liquid flowing per unit time through a pipe of radius R, across which a pressure of P is maintained. Pressure difference is maintained. Then the amount of liquid flowing per unit time, many times represented as dV by dt, this is volume of the liquid flown per unit time, is given by something known as Poiseuille's equation. So according to Poiseuille's equation, the volume rate of flow is given by pi r to the power of 4 into P, where P is the pressure difference, divided by 8 eta L. 8 eta L. So the volume of the liquid flowing per unit time is given by pi r to the power of 4 into P divided by 8 eta L. You may notice that this is nothing but something per unit time, and this can also be written as P divided by 8 eta L divided by pi r to the power of 4. If you look at it carefully, something which is flowing per unit time is equal to some difference divided by some other term. This resembles the equation electric current is equal to potential difference divided by resistance, or heat current is equal to temperature difference divided by thermal resistance. Just like these two equations, this is pressure difference and this is some flowing quantity, and therefore the denominator must represent opposition offered, which is known as fluid resistance. So fluid resistance is nothing but 8 eta L divided by pi r to the power of 4. 8 eta L divided by pi r to the power of 4. So resistance of a fluid, or say fluid resistance, is given by 8 eta L divided by pi r to the power of 4. So Poiseuille's formula gives us the volume of the liquid flowing per unit time. Stokes law is another important law which tells us the viscous force whenever an object is in, or say moving with terminal velocity in a fluid. For example, we can consider, say, a liquid. There is a long column, let's assume, and a steel sphere, or say steel ball, is falling down. Let's assume that the steel sphere is of radius r and it is falling at a terminal velocity vt. Terminal velocity means constant velocity. Then Stokes law tells us that the viscous force is equal to 6 pi eta rv, where v or vt is the terminal velocity. And we can also find out what the terminal velocity is. That terminal velocity is given by 2 by 9 r square into rho minus sigma divided by eta into g, where r is the radius of the steel sphere, eta is the coefficient of viscosity of the liquid, rho is the density of solid, and sigma is the density of liquid. Sigma is the density of the liquid. Thus, we have terminal velocity as given by Vt is equal to 2 by 9 r square into rho minus sigma g divided by eta. Another quantity which is quite important in the present context is what is called as Reynolds number. What is that Reynolds number? It's the number which decides the nature of flow of a liquid. If this Reynolds number is less than 1000, it is treated as laminar flow. And if this is greater than 2000, it is treated as turbulent flow. It is treated as turbulent flow. So between 1000 to 2000, the liquid may undergo turbulent flow or say laminar flow, all depending on the subsequent conditions. This Reynolds number is given by rho v into d divided by eta. So Reynolds number is given by rho into v into d divided by eta. So remember this equation, Reynolds number is generally asked in the conceptual form. So remember the range of values as far as Reynolds number is concerned. Okay, as far as this part is concerned, this is the synopsis part 1, where we have discussed the properties of solid and properties of fluids. Which two properties? Surface tension and viscosity. In the part 2, we will take up the hydrodynamics ideas, where we have hydrostatics, that is fluid statics, and fluid dynamics for our discussion. This is part 2 of concept discussion of mechanical properties of solids and fluids under crash course program. In the first part, we had discussed mechanical properties of solids, surface tension and viscosity. We will take up the discussion of the idea of fluid mechanics, that is generally known as hydrostatics and hydrodynamics. First, we will take up hydrostatics. We will look at the properties of fluids at rest. Later, we will take up hydrodynamics, properties of fluids in motion. So, first of all, the idea of hydrostatics. In this, we will discuss the properties of fluids at rest. Some of the basic properties of fluids are like this. Number one, the basic idea of density. You know that density is nothing but mass per unit volume, and this is applicable both for liquids and gases. In general, fluids is a scalar quantity and no direction is associated with this quantity. Now, density is defined as mass of the object divided by volume of the object, as you can see. For a solid object, that means an object which is not hollow from inside, for a solid, completely solid object, density of the object, or say density of the body, is equal to density of the material from which it is made of. Density of the object and density of the material are equal to each other. While for a hollow object, density of the object or density of the body is generally less than density of the material from which it is made of. This because volume of the object, that is body, is greater than the volume of the material from which it is made of. Simple idea. Suppose I consider the liquids which are mixed with each other. When two immiscible liquids are mixed, then remember the denser liquid is at the bottom while the less denser is at the top. Bottom portion is occupied by the denser liquid. One of the important terminologies which we use here is the idea of relative density or specific gravity. Relative density is represented by RD, specific gravity. This is nothing but density of the object or density of the body divided by density of water. This is also known as specific gravity. Suppose I consider two immiscible liquids, and if I consider liquids which are mixed with each other, not immiscible, let us consider liquids which can be mixed. So, density of the mixture can be understood like this. Suppose we consider two liquids of masses m1 and m2 and their densities are ρ1 and ρ2 respectively. Then the density of the mixture is given by m1 plus m2 divided by m1 by ρ1 plus m2 divided by ρ2, or this can be represented like this: sigma m divided by sigma m by rho, of course from 1 to n. So I can write mi, rho I, mi, and this is from 1 to n. So if masses and densities are given, the density of the mixture can be calculated like this. Suppose two liquids of volumes V1 and V2 whose densities ρ1 and ρ2 are mixed, then the density of this mixture is given by ρ1 V1 plus ρ2 V2 divided by V1 plus V2, or this can be written like this: sigma rho I Vi divided by sigma Vi from 1 to n. That is how you find out the density of the mixture of liquids when masses are given or volumes are given. Suppose we consider the variation of density with pressure. Variation of density with pressure. You know that we can write rho is equal to m by v and rho naught is equal to m by v naught. So if I take the ratio, rho divided by rho naught is equal to, what is it, v naught divided by v. But we know that by definition of bulk modulus P is given by minus v naught delta P divided by delta V. That means V is equal to V naught into 1 minus delta P divided by B. So volume variation with respect to pressure is given by this equation. This can be simplified further. We can write rho by rho naught is equal to V naught divided by V, 1 minus delta P by B to the power minus 1, which is nothing but 1 plus delta P divided by, of course this term remains like this, 1 plus delta P divided by B, or we can write rho is equal to rho naught into 1 plus delta P divided by B. So density as a function of pressure can be represented like this. So the density varies with pressure as given by this equation. Variation of density with respect to temperature. Here, you know that rho by rho naught can be written as V naught divided by V naught divided by. Volume changes as given by this equation, V naught into 1 plus gamma delta theta, or rho is given by rho naught divided by 1 plus gamma delta theta. And for small change in temperature, we can write it as rho naught into 1 minus gamma delta theta. So over small variation of temperature, the density can be varied, or density variation can be represented by this equation. The second important property is pressure. You know, pressure at a given point can be defined by this equation. Suppose I consider small force over small area delta S or delta A, then we can write this as limit of delta F by delta S, or this can be written as dF divided by ds, or many times it is also written as dF divided by dA. So pressure is given by dF divided by ds or dF divided by dA, or many times the average pressure is written as force per unit area. Here are a couple of important points. Let us consider a liquid and atmospheric pressure is P naught, the exposed part is at pressure P naught. Consider a point which is at a depth h, the density of the liquid being rho. Then the pressure at this depth is given by P is equal to P naught plus rho g h. P naught is the atmospheric pressure and P minus P naught, which is rho g h, is given by, or this is known as gauge pressure. Gauge pressure, which is rho g h, P minus P naught, that is the excess pressure over the atmosphere is known as gauge pressure. Remember, even though the pressure is produced by a force that has directional properties and is a vector, the pressure itself is a scalar, and there is no question of direction associated with pressure. It is unique and there is no question of specification of that one. And remember, this pressure acts equally in all the possible directions. That means if a pressure measuring device is at a given point in a fluid, whatever may be its orientation, the pressure measured is same. Pressure always acts normal to the boundaries of the fluid. Remember, pressure is always normal to the boundaries of a fluid. Remember, a very simple concept but quite useful. We also know that according to suppose I consider a liquid which is static. Let us consider a couple of points which are at the same depth. This is H, this is H, this is H, etc. The pressure at all these points, suppose I call these points as X, Y, Z, pressure at X is equal to pressure at Y, which is equal to pressure at Z. Or if you consider, say, connected fluids. If you consider connected fluids, or say connected liquid columns, then the pressure at different pressure inside different liquid columns at a given point are same. For example, if I consider this point, the pressure here, the pressure here are all same. The pressures are all same regardless of the type of the liquid which is present. So remember, as far as the static fluid which is open to the atmosphere is concerned, pressure at A, pressure at B and pressure at C are all equal to each other. So remember this, in the case of connected fluids exposed to atmosphere, at rest the pressure is same at all the points. And you know that this is known as Pascal's law. And remember, it doesn't matter what is the shape of this container, regardless of the container shape, it's the same thing. This Pascal's law can also be represented in the slightly different way. It tells us that if an external pressure is applied in an enclosed fluid, it is transmitted undiminished to every position of the fluid and to the walls of the container as well. So this is what is known as Pascal's law, another version of Pascal's law. One of the very important applications of this fluid is the idea of what is known as buoyancy or say upthrust. Suppose I consider a liquid and if we immerse an object, for example, this is the object immersed. The liquid which is displaced by this object exerts an upward force, and this is what is called as upthrust or buoyant force. This is known as buoyant force. And this is understood in terms of what is known as Archimedes Principle. According to Archimedes Principle, when an object is immersed partly or completely in a liquid, the upthrust or the buoyant force is equal to the weight of the liquid displaced. Weight of the liquid displaced. This is what is known as Archimedes Principle. Very simple principle. The magnitude of the buoyant force is equal to weight of the liquid displaced. that is upthrust is equal to weight of the liquid displaced by the object. And remember, this is applicable both for partly submerged objects or objects which are completely submerged, or an object which is submerged partially in two liquids. For example, this is one liquid, assume, and this is another liquid. Let's assume that there are two liquids and I am representing them like this. Now, if you consider an object which is partly immersed in these two, then there is an upthrust exerted by liquid 1 and liquid 2 respectively. So, the object is under the mercy of both the upthrust exerted by this one, upthrust exerted by the second one. Suppose we consider a couple of applications. Let's assume that there is a container and now we have immersed, we have submerged forcefully an object. That means I am holding this object. What are all the forces exerted? Its weight, I'll call it as mg, and the upthrust which is in the upward direction, I'll call it as wu. So these are the two forces apart from the force holding the object. So if I release this object, at the instant of release, these are the two forces acting on the object. Now, if mg is greater than upthrust, that means if the weight of the object is greater than the upthrust, then the object sinks. It sinks to the bottom till another force, which is in the form of normal reaction, is available. So it sinks to the bottom, and upon sinking the bottom, it gets one more additional force, which is normal reaction, and thus in addition to upthrust, that normal reaction can keep the object in equilibrium. Suppose mg is equal to upthrust, that means its weight is equal to upthrust, then the object is already in equilibrium and it remains submerged or say immersed in that position. It doesn't move up or it doesn't move down. If the weight is less than the upthrust, what happens? That means weight is less than the upthrust. What happens now? You may notice that there is a net upward force on the object and therefore it rises until it is partially submerged. It is partially immersed or say partially submerged. So if I hold something submerged in an object or say liquid and release it, these are the three possibilities. If the weight is greater, then the object sinks. If the weight is equal to upthrust, then there is no change, it remains suspended inside the liquid. And if the weight is less than the upthrust, the object starts rising up until it is partially out of the liquid and it gets an additional, or rather it starts floating partially submerged. So this is how you analyze the three cases of the object submerged inside the liquid. Some important applications are like this. Suppose I consider this interpretation in terms of density. The object's density is rho, it is solid, assume that it is solid from inside, completely solid, there is no cavity or there is no say vacant space, and the density of the liquid is sigma. Now, if the density rho is greater than sigma, then the object sinks. If rho is equal to sigma, it remains submerged. and if the density rho is less than density of the liquid, it rises and starts floating partially submerged. So these are the three important cases to be kept in mind. There are some important applications of Archimedes principle. Let's see what are all those. Applications of Archimedes principle. Number 1, finding relative density of a solid or an object. You know, relative density is given by density of the object, density of the body, divided by density of water. So I am going to write this as weight of body divided by weight of equal volume of water. So further simplification, weight of body divided by weight of equal volume of water is nothing but upthrust. Weight of body, upthrust is nothing but loss in weight of weight in water. So how do I write this? Weight is W naught divided by W naught minus weight in water. Loss of weight in water is nothing but its actual weight minus its weight measured in water. So relative density can be calculated simply by measuring its weight first in air, and we can find out what is its weight in liquid and then taking the ratio. So relative density of the solid can be calculated like this. Second, relative density of a liquid. Relative density of a liquid can be represented like this. You know, the upthrust can be represented. So it's suppose I write it like this. Loss in weight of an object in water is A, and let's consider, I'll write it like this. Loss in weight of the body in water is A. Loss of weight in liquid is B. So what is that? So then the upthrust is equal to V sigma of water into G, and upthrust, this is in water, this is in liquid, V density of liquid into G. This is equal to A, this is equal to B, this is equal to A. So I am going to take the ratio. If I take the ratio, what do I get? Sigma L divided by sigma of water is equal to B by A. But you know, B is the loss in water, so I am going to write it as W naught minus weight in liquid, W naught minus weight in water. So the relative density, that is sigma L divided by sigma of water, that is the relative density, is simply its weight in air, actual weight, minus weight in liquid, its weight minus weight in water. So relative density of the liquid can be found out using this expression. Third, to determine volume of a cavity. To determine the volume of a cavity in a body. Suppose the weight of the body in air is say W0 and the weight of the object in water is W, represented like this. So, I can write volume is equal to loss in weight divided by sigma into G. That is nothing but the upthrust equation. That is nothing but W0 minus W of water divided by sigma into G. While the volume of material of the body is equal to V0, which is nothing but mass of the body in air divided by density of the material. So, we can calculate this. Therefore, volume of the cavity is equal to V. This is nothing but V volume V minus V0. So, we can subtract one from the other and we can find out like this. So, we can find out the volume of the cavity using this concept. And one more, determination of impurity. Determination of impurity in a given metal. Suppose a solid of mass m contains impurity, assume it to be Y, and its density is ρ1. What is ρ1? This is of density ρ1. Impurities of density, say, let's assume that density of the pure material is density ρm. I'll call it as ρl. Then we can write volume of impurity V1 is Y divided by ρ1. Volume of pure metal should be Vm is equal to, I'll call it as Vm, which is m minus Y divided by ρm. So, total volume V is equal to V1 plus Vm. That's the total volume of the body, which is Y by rho L plus m minus Y divided ρ1, that is, divided by rho m. But I'll call this as equation 1. But we can also represent the volume like this. Volume is equal to W0 minus its weight in water divided by sigma. That is density of water. So, this is your equation number 2. Now, we can equate 1 and 2, and if I equate 1 and 2, we can calculate the value of Y. So, it's basically a question of substitution now. So, the extent of impurity of a material present in a pure metal can also be calculated like this. So, these are some important applications as far as Archimedes principle is concerned. Suppose I consider the case of equilibrium of an object in a liquid or inside a fluid. How do we do this? Suppose I consider, say, something like this. A liquid is present here and a floating body is slightly tilted from equilibrium position. For example, there is an object, let's assume that this is a cube which is present like this, and I rotate it slightly and release. What happens? Then the center of buoyancy shifts to a new position. And then, for example, here the center of buoyancy shifts to a new position. It was here, and then upon rotating, the center of buoyancy shifts to a new position like this. And the vertical line passing through the new center of buoyancy and the initial vertical line meet at a particular point called metacenter. This is what is known as metacenter. Now, if the metacenter is above the center of gravity, then the upthrust tends to bring the body back to its original position. That means for rotational equilibrium, remember, the metacenter must be above the center of gravity. Otherwise, what happens is that the torque will pull it down and it gets shifted and the object topples. That means if the metacenter goes below the center of gravity, the couple formed due to the weight and the upthrust tend to topple the given object. So remember how to represent this idea, that is the idea of the rotational equilibrium of a given object. Rotational equilibrium is possible only when this condition is met. So these are some key ideas as far as the liquids at rest are considered. The key ideas are very simple. Learn the basic ideas of Archimedes Principle and the laws of flotation. Let us now consider the ideas of hydrodynamics, that means fluids in motion. Here we consider a fluid which is in motion. The two key ideas in this chapter are, or say in this concept are, mass conservation principle and energy conservation principle. These are the two key ideas as far as this chapter is concerned. Let us consider, say, a pipe of varying cross section like this. Let's assume that A is this cross sectional area. The speed of the liquid which is entering here is V, or say we will call it as A1 and V1. Liquid comes out from the other cross section at a speed V2, cross sectional area being A2. And the same thing happens everywhere also. If I consider this cross section as A, and the fluid which is coming out here is coming out at a speed V, then the density of the liquid rho, as you can notice, remains constant everywhere, which means that the volume of the fluid flowing per unit time should remain constant. So if I consider a small extent of liquid which is flowing here, whose length is say some delta x, and the liquid takes time delta t to cross this one. So clearly volume of the fluid, mass of the fluid flown per unit time should remain constant. So I'll write dm divided by dt is equal to constant. What is that dm by dt? d by dt of mass. Mass, you know, is density into volume. So I'm going to write it as rho a into x is equal to constant, or we will write as rho into a into dx divided by dt is equal to constant, or we can write rho a dx by dt can be calculated over a length. I can write as delta x by delta t, or I can write rho A into V is equal to constant, as this delta x by delta t is nothing but velocity. Or I can write rho 1 A1 V1 is equal to rho 2 A2 V2 is equal to rho 3 A3 V3 etc. is equal to constant. Now, if I assume that the density of the liquid remains constant everywhere, we can say rho 1 is equal to rho 2 is equal to rho 3 etc. and that is rho, or we can simply write AV is equal to constant, or A1 V1 is equal to A2 V2 in the previous diagram that is shown. So AV is equal to constant, and this is what is called as principle of equation of continuity, according to which the total volume of the total mass of the liquid crossing a given pipe is constant with respect to time. But if you ask what does that AV give you, observe it carefully, A into delta x divided by delta t. But you know, A into delta x is nothing but volume. So this is nothing but delta V by delta t is equal to constant. It tells you volume flow rate. So this is nothing but volume flow rate. So equation of continuity can be interpreted as mass per unit time is constant or volume per unit time is constant. Any of these two representations is perfectly fine. If you are talking of constant density, then volume flow rate remains constant is a better description of the given situation. The second is energy conservation, given in the form of Bernoulli's theorem. According to which, in the case of a steady flow of incompressible and non-viscous fluid through a tube of non-uniform cross-section, the sum of pressure energy, potential energy and kinetic energy per unit volume is constant. For example, you can consider a liquid flown in a pipe. Now, I can say this is of cross-sectional area A1. Liquid enters this at a speed V1 and this is at a height H1 and the pressure here is P1. Likewise, A2 and V2 are the quantities here, P2 is the pressure over here and H2 is the height of this. So here what it tells is pressure energy plus kinetic energy plus potential energy is constant. Obviously, in the case of an incompressible fluid which is not undergoing any rotation and there is no question of viscosity, then PV plus half mv square plus mgh is constant. Now if I divide by V throughout, what do I get? If I divide by V throughout, then P plus half rho V square plus rho GH is equal to constant. This is what is known as Bernoulli's theorem. Many times this is written as P1 plus half rho 1 V1 square plus rho 1 GH1 is equal to P2 plus half rho 2 V2 square plus rho 2 GH2. This is constant. If the liquid is flowing at the same horizontal level, then even rho GH becomes constant. That means if H1 is equal to H2, we have P1 plus half rho 1 V1 square is equal to P2 plus half rho 2 V2 square. That means we can also write it like this: P plus half rho V square is equal to constant. That's right. So we notice that if the velocity is large, pressure is small. and if the pressure is large, velocity is small. So when a fluid flows from broader to narrower pipe, the velocity increases and thus the pressure decreases. So remember, this is a key concept which should be kept in mind. So let me repeat it. When a fluid flows from broader to narrower pipe, wider to narrower pipe, velocity decreases. Velocity decreases from continuity equation. If the velocity decreases, then the pressure decreases, right? Velocity increases and the pressure decreases. The various applications of Bernoulli's theorem, for example, whenever in a high-speed storm, the roofs of the houses detach themselves, right? They blow off. This is because pressure below the roof is atmospheric pressure, while above it is very high. So low pressure because velocity is high and the pressure is less, and thus due to this there is an upward pressure exerted and thus the roof is lifted up and it goes off. Or if you consider two closely parallel moving boats or buses or trains, then what happens is that between them the pressure decreases, right? Because the velocity is very high and thus the pressure decreases. And as the pressures decrease, there is a pressure difference which is created towards each other and they try to push, or rather they are attracted or pulled towards each other. So there are some applications of Bernoulli's theorem in daily life. One of the very important applications is what is called as speed of efflux. Speed of efflux. So what is that speed of efflux? We take a container and let's assume that liquid of density rho is filled here and a hole is made at a depth h below the free surface. There is a hole which is made at a depth h below the free surface. Then the liquid oozes out, it comes out, and the speed with which it comes out is called as speed of efflux. And the speed of efflux is given by square root of 2gh. Speed of efflux is given by square root of 2gh. So now, as you can notice, if I consider couple of orifices or say holes, for example, this hole is at a depth h1, another is at a depth h2, etc. Then this liquid comes slowly, this liquid is faster, etc. So V1 is equal to root of 2gh1, V2 is equal to root of 2gh2, etc. Now as h2 is greater than h1, the speed with which it comes out is more than the speed with which the top fluid comes. Suppose this liquid is at a hole is at a depth h and the liquid column is of depth h. That means this is h minus h. Then we can find out the time required by this, the time required by the liquid to reach the base level can be found out. And the range of the liquid flowing from the orifice also can be found out. Suppose I consider the hole is at the bottom of the tank. Let us assume that in one more case, the hole is at the bottom of the tank and the tank is of depth h. then the time, suppose this is of area A naught, the free surface is of area A. Then the time required for the liquid to come to the bottom of the tank, that means the time required to empty the tank, is given by A divided by A naught square root of 2h divided by g. So this is the total time required by the liquid to fall from a height h, or say height 0 to bottom h. So this is how you find the time required to empty the container. We can also find out the time required by the liquid, this is h, the time required by the liquid to strike this point, the range, etc. As the vertical velocity of the liquid at the orifice is 0, suppose I consider the vertical velocity, vertical velocity is 0 at the beginning, right? And therefore, the time taken by the liquid to reach this level, so the liquid which falls off, strike this level, it is as good as free fall. So the time required by the liquid which is coming out, I repeat, the time required by the liquid which is coming out to reach this bottom level is given by square root of 2 h minus h divided by g, this height being h minus h. So the liquid which is coming out takes this time to reach the ground level. And we can also find out the range. Range is equal to velocity into time taken. Velocity is the speed with which it comes out, and the speed with which it comes out is horizontal, velocity is horizontal, and that is given by square root of 2gh. The time taken is the same both for horizontal and vertical motions, that is 2h minus h divided by g, or you can simplify it further and this becomes 2 root h into h minus h. And this range clearly is maximum when h is equal to h divided by 2. That means if the hole is punched at the midpoint, then the range of the liquid coming out is maximum. This range is same whether the hole is at a depth of h or h minus h. You may notice that the range is same whether the hole is at a depth h or at a depth h minus h. So you may notice that the same equation tells us the same thing, this equation tells us the same thing, because the range is given by 2 root of h into h minus h. Whether this is taken as the depth of the hole from the top or h minus h is taken as the depth of the hole from the top, in both the cases the range remains the same. So it is regardless of this idea. That means whether the hole is punched at a depth of h from top or at a height of h from the bottom does not matter. The range is same in both the cases. So these are some key ideas as far as hydrodynamics is concerned. Remember, it is a pretty simple concept. The two important concepts are mass conservation principle and energy conservation principle. So in both the cases, the conservation principle is put into use, and remember the equations which are quite useful in this chapter. In our next session, we are going to take up numerical problems based on the concepts that we have learned. Thank you very much.